Okay, so let's chat about one-to-one functions. Without even me telling you what a one-to-one function is, let's talk about these two diagrams, and I'll ask you some questions about one-to-one functions. Just based on that phrase, one-to-one, here are two functions. There's f and there's g. They both take a domain A, and they map it to a range B. So what's the domain in each case? What's the only, if you had to describe the domain, how would you describe A? What is A?
X such that X equals...
Well, we don't even know if it's X. We don't know if it's Y. I haven't given you a label for it. So X is this. What is the set? 1, 2, 3, 4. That's all you can say about A. That's what A is. Let's call this one, let's do, this is B1 and this is B2. What is B1? 2, 4, 7, 10. It's common to write them in ascending order. It's easier to find the values that way. And what's B2 going to be? 2, 4, 10. And that's, I'm missing one already. 2, 4, 10. Absolutely. Okay, so we have, in this case, this is the domain in this case, and here are the two ranges. Are both of these functions one-to-one? Is one of them one-to-one? Is one of them not one-to-one? I haven't told you what the definition is, but do you want to take a guess here? Yeah. What do we think? We think this one is one-to-one? What about the second one?
It's 2 to 1.
That's nice. It's fun. I like not giving the definition and seeing what new words. There's no such thing as a 2-to-1 function, although I think we should just invent new math terms to fit what we want, which is fine. Mathematicians do that all the time. When they find a new field, they just have to invent new terms. It's kind of neat. Just in any science you do that, actually. Just rarer in math, I guess. Does anybody want to try to tell me why? Now, I will tell you that, yes, the first function f is one-to-one. The second function is not one-to-one. Can anybody tell me why? Why? Raise your hand and explain it. Shh. Hands? No one's speaking it. Baldwin. So there are two different values from the, what is A? So there are two values from the domain that what? Yeah, the word you're looking for, it's a better word than correspond. You can call it map. So what does function f do? It takes 4 and it maps it to 10. It takes 3 and it maps it to. It takes 2 and it maps it to 1 and maps it to 2. It maps. That's what those arrows mean. So you could say G, this is what we're going to say, so is not 1-to-1 because what?
Because two domain values map to 1 line.
Two different, you can say input values, that's fine. Map to what? The same output value. Good. So let's look at this function right here. We have a table, hour and population. Do we have any units on this? I don't think there's any units on this table. It's not really super important, but we have time and hours, 0, 1. It's pretty constant. I mean, it's the constant interval. And then we have the population. Based on this data set, strictly just looking at this data, do you think this function is one-to-one?
Yes.
Just based on this data set. If you plotted this data set, what does this function always do? So you have time here, and then you have n, the population right here. It's always what? It's always increasing. That's correct. So if we go back and we found out why this function is not one-to-one, does anybody want to venture a guess as to what it means for a function to be one-to-one? Raise your hand. Yeah, Olivia? No, if it is one-to-one, what is it going to be?
There's
Always what? Or, yeah, so there's many different ways to say the same thing here. So we're going to say, one way to say this is one-to-one. A one-to-one function is always increasing or decreasing. Is it possible for a function to not be increasing and not be decreasing? Sure, what kind of function is that called? No, it's increasing and decreasing. It can be both, and it would definitely not be 1-to-1. But is it possible for a function to not be increasing or decreasing anywhere? Yeah, it is. What kind of function is it? Y equals 4. What kind of function? There's a name for that kind of function. It's not moving, so it's always what? What? Constant. A constant function is either increasing or decreasing. Can a 1-to-1 function be constant? No, it has to always be increasing or decreasing. Why? Well, let's just take a look at that. Let's say we had a function y equals 4. So when x is 3, what's y? When x is 5, what's y? 4. So we have two different inputs mapping to the same output. If a function is constant for any part of its graph, so let's say we had a function that went like this, for a little bit, and then went up like this. Let's say it was constant right there. How many different x values are there between here and here? Infinite number of x values. So how many different x values map to the same y value? Infinite number. Is this a 1-to-1 function? No. The terms get a little murky depending on what book you look at, depending on what teacher you have. I'm confused by it sometimes because the way I was taught, always increasing or always decreasing means strictly increasing or decreasing. The word that I was always taught is strictly increasing or decreasing. Sometimes when I give you pages from books or texts or articles, when you need to be aware of this. If a function is increasing, or if it's said to be increasing or decreasing, that can mean strictly increasing or decreasing. I was taught in my math education that there was a difference between the two, just in how it's described verbally. Strictly increasing means it's always going up or always going down. Increasing could mean it levels off for a split second. When you see it written in texts, just be aware and check. Does the book mean, does the article mean, does the teacher mean by increasing, decreasing, can it level off? When I say it, I'm going to try to be this specific. It is always increasing or always decreasing. If I say decreasing, it could level off. Just be careful in written text. Sometimes decreasing means strictly decreasing. Sometimes increasing means strictly increasing. Yes?
If you have a V shape.
Ah, if you had a V shape. So what is this right here? Like this? Well, let's think about this for a sec. So this value, I don't know, that could be x equals 2, and this one could be x equals 4. This is now, I don't know, y equals 7, right? Is that a 1-to-1 function? No, because both 2 and 4 map to 7. In fact, how many different pairs of x values map to the same y value? Except for this middle one, right? If it's a symmetric, this would be maybe an absolute value graph.
We can do the...
So let's look at this another way, though, okay? Let's look at this another way. Let's look at the data set reversed. Let's look at the data set reversed. So if you had a data set like this where you had time and then population, that would mean if you had a specific time, you would want to find out what the population is. If you flip this, why would that be useful? If your input became population, your output would become time. What would that be helpful in helping you determine? Well, it changes the question you're asking. It changes the question you're asking. What? Well, think about it this way. If the first data set, this first one, if you had a time, it tells you the population. But let's say you didn't have the time. Instead, you had the... What could you use this function to tell you? The time. To tell you the time. So this is the introduction to this second part of this unit, which is if you take a function, if f goes this way, going from time to population, if you go backwards, does anybody know what that's called? We're going to be generating what types of functions? If you do it in reverse, what's that function called? The what? Ah, yes. So semantically, you might call it a reverse function, which could actually is pretty accurate. It's like the word reverse. It's going to be called the what? Inverse functions. We're looking at inverse functions. So let's say you had a really easy time. Let's say you knew a really easy time measuring population, but not necessarily time. With this function right here, you could input a population and it would tell you how long the population has been growing for. Okay, so this one right here, is this a one-to-one function? Just from the data you see, is this a one-to-one function?
Yeah.
Yeah. If we graph this, is it necessarily a one-to-one function? These are, how many points do you have here? You just have 8 points, right? Is population growth a continuous function? Meaning, can you graph it without lifting up your pen? Yeah. Is it possible for population to instantaneously change? Kind of, because you can't have half a person, right? Right? It instantaneously changes, like you have a person and then you don't have a person, or you don't have a person and then you have a person. Logistically speaking, are there a lot of other points? Can you get from 100 directly to 168? Not if it's growing from inside that population. In realistic terms, is it possible for that to happen in terms of a country? How could a population of a country go from 100 to 168 instantly? Immigration, right. But let's just say this is a growing population from a petri dish of bacteria, for example. Is it possible for it to instantaneously change between more than one bacteria? No, it's not. So are there lots of other data points in here if you were to graph this? Yeah. So just because these data points constantly increase, what could happen inside those data points? It could fluctuate, right? So it could go like that, right? Sure, and it's strictly increasing. But let's say I have these points. These points themselves are strictly increasing, but what could happen in between?
They level off.
Anything you want. Everything you just said. It could level off. What else could it do? It could decrease, and then it could increase. It could spike. It could oscillate, right? You could have something going woo, doo, 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 woo. In terms of population growth, is stuff like this possible? Sure. If you were looking at the population of a country, is it possible for population to drop suddenly?
Yeah.
Yeah. What could do that?
War.
War, natural disasters, a crisis. What does it mean if a population suddenly spiked? What could that mean? A bunch of people could have immigrated to the country. What else? In the natural, more people, the fertility rate changes. What's a factor that can contribute to sudden population growth? So for example, population growth was, I don't remember, was pre-18th century, but all of a sudden in the 18th century, population globally started really rising. The Industrial Revolution. Why did the Industrial Revolution raise the population across the globe? Why? What did technology do that allowed the population to grow? Yay, we could print more Bibles, but that didn't really increase the population. What could we do that increased the population?
A lot of people go more places.
A lot of people go more places, but that meant that we could spread, sure. But what else? What's the primary limiter in terms of a population? What? Food. Thank you. If you don't have food, you can't have more people, right? What did the Industrial Revolution allow us to do? Yeah. Industrial Revolution and the ability to, it used to be, I remember the statistic I read, 250 years ago, it took 19 out of every 20 people to produce enough food for 20 people and for export. Do you know what it is now? 1 out of 20. So 250 years ago, it used to take 19 out of 20 people to produce enough food for everybody, the 20 people, and to produce food for export at a given country. Now it's 1 out of 20. And as another interesting note, even with the Industrial Revolution, it was one particular chemical that allowed the population on this planet to explode. Anybody know what that chemical is? What? You're really close. You're really close. Begins with an A and an N. Ammonium nitrate. What is that? No. What do you need in order to grow crops? What is it? What? We're like in the most agricultural dense population on the planet. What is it? It's a fertilizer, yeah. Without ammonium nitrate, there's no way the global population would be where it is. No way at all. Ammonium nitrate is ridiculously easy to make. It is cheap.
Agriculture go better.
Absolutely. It increases yield, makes things grow faster, stronger, harder. Kanye West in math class. Okay, so you can read about ammonium nitrate. It's very interesting. Without ammonium nitrate, we would not have a population to just say there's no way at all. Then again, I can't say that for certainty because maybe someone would have figured out something different, but fertilizer is important. So we have this right here. So here's this function right here. Is that a function?
Yeah.
Absolutely. Why?
Across the
Oh, there's a little harmony right there. I like that. It passes the vertical line test. I like that. Is that a one-to-one function? No. All you need are 2 points to map to the same, 2 inputs to map to the same y value, and it's not a one-to-one function. How many different x values map to the same y value? Yeah, in math, there are only 3 numbers of answers. There's either none of them, One of them, or how many different pairs of x values map to the same y value? An infinite number. An infinite number. That is definitely not a one-to-one function.
So it's kind of like one-to-one function. It should cross the vertical, horizontal line.
Ah, there we go. So now we have a
Horizontal line.
horizontal line test. So what I'm going to do is I'm going to paste this in because I always mess up the writing of the horizontal line test. I'm just going to bring it in here. I'll bring in both here. So first is what we talked about right here. There's this one. A function is called one-to-one if it never takes on the same value twice. That is, if f of x1 does not equal f of x2 whenever x doesn't equal x2. Meaning, if you take two different x values, what are you always going to have? Two different y values. Exactly. I'm going to actually move this down. So yes, if you have two different y values, it had to have started from two different x values. You can never violate this. So two different y values are not equal if x values are not equal. So the horizontal line test is going to be this right here. Says that a function is one-to-one if and only if a function is one-to-one if and only if no horizontal line intersects its graph more than once. No horizontal line. So if you can draw a horizontal line that passes through the graph more than once, you know the function is not one-to-one. Exactly. So the key thing is if and only if. Has to, must, both ways. Meaning if no horizontal line intersects this graph more than once, it is a one-to-one function. And if it's a one-to-one function, no horizontal line passes through more than once. Does that make sense, everybody? So how many horizontal lines do you need to prove something is not one-to-one? Just one. Well, just one. There could be an infinite number, yes, but you just need one. So as long as one doesn't, as long as you have one horizontal line that passes more than once, it is not one-to-one. To prove that it is one-to-one, that's different. We're not there yet. So is it easier to prove something isn't one-to-one? Yes, it is. Proving the negative in general is going to be a lot easier because you generally have to have one case. But proving the affirmative, are you going to be able to test every single output value? No. Are we going to? So is it possible for you to do this in like a list fashion? No, you can't just sit there testing, okay, I'm going to test this x value, and this x value, and this x value, and this x. How many x values are there in functions? Yeah, so do you have enough time? No. So do you have to have something else to use? Yes. Okay, let me just get back to right here. So here is just a nice graph for you to have in your notes. I don't know why it's, let's just cancel that. That's going to close. Let's do this. So on this function right here, is this function one-to-one?
No.
It is not one-to-one because at x1 and x2, f of x1 equals f of x2. When you plug in x1 into the function, what do you end up with? You're at the same horizontal line as if you were at x2. Looking at this graph, are there other such pairs? Yeah, there's a whole bunch of them, right? There's a whole bunch of them. In fact, judging by what this looks like, if this kept on going down and this kept on going down, every single x value except for one of them would have a corresponding x value that maps to the same one. What's that one value that would pass? Yeah, or you could call this the maximum point. It's not necessarily, if this was a quadratic, you'd call it a vertex. You'd call this right here a local maximum. It's also a absolute max, which is just a terminology for calculus. Because could this function go up like this? Do you know if it does? It could, right? This is a local maximum because in this neighborhood, is it the highest point? In the immediate vicinity, is it the highest point? Yes, it is. But we would need to know more about the function. What does absolute maximum mean? It is the maximum of all of them. Do we have enough information to tell that conclusively? No. Could this function bend up? It could. It could. Okay, so let's get to some specific questions here. Is the function f of x equals 1? When you actually do it out, is it 1-to-1? Well, you know from your sketch here, when you graph it, does this function ever turn around? This function is it always increasing? No, but it's only static at one point. Where is it static? 0, 0. Right, exactly. So is this one? Would you say this is 1-to-1? Yeah, the way you could say that mathematically is, you can say this: if x1 does not equal x2, then x1 cubed does not equal x2 cubed. You could say it like that, and that's enough because I will believe you. That is mathematically sound at this point in your math career. At this point in your math career, that is mathematically sound. In calculus, you will be able to prove that this is always increasing. Not quite there yet. Let's go to another example. Don't say this out loud. I'll call on you. Think about this. Is x squared 1 to 1? Let's go with Thistle. What do you think? No, it's not. This thing turns around. Not 1 to 1. How many horizontal lines do you need to prove something is not 1 to 1? Exactly. You just need 1. So you just need 2 x values. So in this case, pick 2 x values that are going to have the same y value for x squared. Pick 2. 1 and 3 and 5. 3 squared is not 5 squared. But negative 1 squared and 1 squared are both 1, right? So another way to say this is, if x1 equals x2, then x1 squared does equal x2 squared. Example, 2 and negative 2. 2 squared does equal negative 2 squared. And you can draw it like this. You could say that that right there is x equals negative 2, and this is x equals 2, and then that would be 4. Does that make sense? It turns around. If the function turns around, is it 1 to 1? Oh, it's not. Let's do another one. Oh, look at that. There it is. Okay. It's pretty easy to tell now that I've done this, but strictly increasing means it's always increasing. Strictly decreasing means it's always decreasing. So strictly increasing, strictly decreasing. Please remember that. So what about inverse functions? We touched on this before with our tables up here. We said it might be useful to know, instead of going from time to population, from population to time. Notationally, f to the negative 1 is pronounced f inverse. That is f inverse. You don't say f to the negative 1. In math, there is overlap of notation. The same symbol can mean multiple things, and they are very different. In this case, does this mean 1 over f? No. This means f inverse. A function f could take values from a, the input set, and map them to b. So it could take a value r and map it to s. What does f inverse do? Yeah, so it takes f, goes f of r is equal to s. But what does f inverse of s equal? R. You can think of the inverse as undoing the function. You can think of the inverse as undoing the function. What does this look like written out properly? Looks like this. Let f be a 1-to-1 function whose domain A and with domain A and range B. Then its inverse function f to the negative 1, I'm going to say that out loud, but that's not how you're supposed to say it, has domain B and range A and is defined by the inverse of y is equal to x. Does anybody know what that symbol means right here? Yeah, it means if, IFF, which is the same thing as if and only if. Both of these things have to be true here, meaning f inverse of y equals x if and only if f of x equals y for any y in B. Meaning, if a function only undoes some of the values, is it the inverse? No. What that means is, so this r goes to s. How many other values could there be? There could be how many other values? And f maps them all to somewhere in B. What does f inverse have to do? It has to undo all of them. If it only undoes part of them, is it the inverse? No, it's not. So let's just throw out a concrete example at this point. So let's say I gave you this function. F of x is equal to 2x minus 3. Is that a function?
Yes.
Is that a one-to-one function?
Yes.
Why?
Because
It's always increasing. It's got a slope of 2, right? All lines except for constants are increasing or decreasing, right? So, for example, what's f of 1? Negative 1. What's f of 2? What's f of 3? What's f of 4? 5. So we have a table of values. Here's x and here's y. We plug in 1, we got 2, we got 1, 3, we got 3, 4, we got 5. Good. Okay, so the function f takes f and it takes x and it maps it to y. What does f inverse do? Yeah. If you plug in 1, you get out negative 1. If you plug in 2, you get 1. But what does f inverse do? If you plug in negative 1, what do you get out? 1. Find me f inverse. Do that now. Play around for a second. You need an equal sign. I need a function. So what do you think it is? So y equals. So when you plug in the y values in for x here, when you plug them in, so you think the inverse function is going to be something like this. F inverse of x is going to be x plus 3 over 2. So you add 3 and then you divide by 2. Let's try that. Add 3 to 1 and you get. Divide by 2 and you get. Add 3 to 3 and you get. Divide by 2 and you get. Add 3 to 5. Divide by 2. Add 3 to negative 1. Divide by 2. So did it work? Yeah. How'd you get that, Baldwin? Yes, it is the inverse. That is correct. Do you have a process that you could duplicate? No? Anybody come up with a process? It's okay if you didn't, because I'm going to teach it to you. You could graph it. You take the function from the graph, absolutely. So you could graph it. Now this was nice because what type of function is this? Is that about as simple as it comes? Could this get a lot nastier? Yeah. So you're always going to be able to graph it? You're always able to, but is it always easy to find the function based on a graph? Yeah, how'd that cubic go on the benchmark yesterday? Oh, yeah. You didn't like that, huh? Not that nice. It's okay. Here is the process. It's really, really straightforward, and you'll like it. Oh, let me get it here. I'm going to find it right there. There it is. That's what I wanted. Write y equals f of x. Solve the equation for x in terms of y, if possible. So write the equation y equals f of x. So do we actually have a function here? What was it? It was y equals what? 2x minus 3? There's step 1. What's step 2 say? Solve this equation for x in terms of y. Let's solve for x. What do I do first to solve for x? What? Yeah, so what do we get? Y plus 3 is equal to? So what does x equal? 2. To express f inverse as a function of x, interchange x and y. The resulting equation is y equals f inverse of x. So what do they mean by interchange? Switch. Just switch. So step 3 is going to be our inverse, f inverse of x will be x plus 3 is equal over 2. Do you have to switch at the end? You could switch the variables at the beginning if you wanted to. Either way is fine. So let's do another simple example. Let's say you had y equals 3x minus 1. If I wanted to find the inverse, what do you do first? I was taught you could switch first, but it doesn't matter. Either way. I will accept both. I will accept either way. So let's solve for x. So what does 3x equals y plus 1, right? So what does x equal? 3. So f inverse of x is going to be x plus 1 over 3. So that was, we switched here. Let's do the same thing, but instead of switching there, we could switch at the beginning. If we switch at the beginning, you have x equals 3y minus 1. Now you solve for? Yeah. So what do you end up with? X plus 1 is equal to? which tells you that y is equal to, so f inverse of x is equal to x plus 1 over 3. You repeat the same process. The only thing that changes is the function you start with. Let's try something a little bit more interesting. So what about f of x is equal to x cubed? Have we looked at that one before? We just did, right? Is it 1-to-1? Mm-hmm. So if we do you like switching first or last? You want to switch last? Okay, so we have y equals x cubed. We need to solve for, hold on, we need to solve for x. So we have x is equal to what? The cube root of y. So therefore f inverse is going to be, f inverse of x is going to be the cube root of x. Sure, absolutely, that's great. Let's graph these for a second, okay? Let's actually graph these. I'm going to pause this. So there's x cubed, and there's the cube root of x. That's pretty cool, huh? So let's graph some different ones though. I'm going to turn this off. I'm going to turn both of these off. What was the first one we had? We had 2x what? 2x minus 3, right? And what was our inverse of that? X plus 3 divided by what? We're sure about that? Let's graph this. Our window's going to need to be a little... Oh, let's zoom out a little bit here. Let's zoom... let's go to window, and let's make it -6 to 6. Let's make it -6 to 6, and let's graph this. There's our original function, and there's the inverse. So let's take a look at the relationship between the function and its inverse. So this right here is... Let's do this. The function and its inverse. Here's 1. And what was the other one we had? Let's go back and go to y equals. And instead of those two, I'm going to turn these two off. And I'm going to turn this one on, and that one I'm going to graph this. I'll tell you now that there is a common relationship between each pair. Wow, so there you go. Hold, let's pause for a second. You zoned in on something that's really important there, Denise. You zoned in something very important. Here's a function and its inverse. Here's a function and its inverse. Let's look at the intersection. That's a great thing to look at. Very good. So let's look at the intersection. We have an intersection here. We have an intersection here and here.
Oh no, and there's a 0.
What are those? And it's 0 here. Thank you. So that one has 3, that one has 2. There's a commonality about the intersection. The intersection happens where? Yeah. Because if 5 maps to 5, 5 has to map to? Yeah, so if the function f takes 5 and puts it to 5, what does the inverse do? It takes 5 and it maps it to 5. So let's do this on these graphs here. Let's put in y equals, what should I put in? What graph should I put in fifth? Y equals x. Look what happens. Window, let's change it to -4 to 4, just so we can get a better curve here. -4 to 4. We graph this. Take a look. Cube roots are obviously takes the calculator a little while. Look at that. If we want to see even better here, let's make it from -1.5 to 1.5. Let's go to -1. I'm just zooming in a little more so you can see this. 2. You see how the graph is changing down below? That's pretty cool right there. Did I graph that right? Yep. A little smoother curve. Do you understand why it intersects at y equals x? If a function takes a and maps it to b, what does the inverse do? It takes b and maps it to a. So what happens if a maps to a in the function? What does the inverse do? It stays the same. It doesn't move. So here's the question I have. If this point right here, I'm going to clip this in. This is the big thing I want to clip in here. Here's a nice zoom here. It's a nice picture. You like that? I do.
Yeah,
It's a nice picture. If I have this point right here, let's say, is that on the line y equals x? It's not. That point, we'll call that point AB. If AB, and actually let's do it on the original function. Here is AB. If AB, so A is right there, and B is right there. Everybody sees the values? If AB is on the original graph, what point has to be on the inverse?
BA.
BA. So where's BA going to be? Well, BA is going to be right about there. Because this distance has to be what? That distance is A high, and this distance is B over.
It can be the y equals x, that line is a reflection.
Here we go. So let me give you a good picture. Let's give you a good picture of this. Look at that, good picture. Here they are. So let's do a new one here. It's a whole example here. So here's a better picture here. So here's a function, x cubed plus 2. There's x cubed plus 2. If you wanted to visually graph it without actually plugging it into your calculator, look what you can do. If you have the point AB, what else do you have to graph? BA. And here's the relationship that's where the reflection comes into play. Do you see these two triangles right here? That's what kind of triangle is that? Right triangle. What is this right here? You can use geometry, and what can you prove? You can prove that the distance from here to here is equal to the distance from there to there. And you can also prove that this... Excuse me. You can prove that that's a right angle. And you can prove that this is a right angle. So if you have right angles in the same distance, what do you call this? This is a reflection across the line. What is that yellow line? It's a reflection over y equals x. So what can you actually do to find the inverse? You could take your piece of paper and fold it over y equals x. You could with your pencil, and then you get the outline of it. It's a reflection over the line y equals x. And here's the question I have for you. What happens if you take a horizontal line and you reflect it over the line y equals x? A horizontal line will become a...
vertical.
Yeah, it'll become a vertical line. If you take a horizontal line and you reflect it over y equals x, let's try that here. Here's y equals x. Here is a... Hold on to your pencil, please. Y equals 4. If I reflect that over the line y equals x, what does the line become? It becomes a vertical line. What's the equation for it? X equals 4. These are reflections, right? And what's the reflection of x equals 4? Y equals 4, right? But if you do a horizontal line test, that tells you if the function is a one-to-one function. If you take that whole function and flip it over y equals x, horizontal lines become vertical lines, right? So when you're testing a function to see if it's one-to-one, you're actually testing to see if its inverse is a... Yes. The reason our functions have to be one-to-one in order for them to have inverses is if a function is not one-to-one, its inverse is not a... Yes, I'm going to write that down. If a function is not one-to-one, then its inverse is not a function. Why? Horizontal lines become vertical lines when they are reflected over the line y equals x. I'll make that bigger for you to see. Is that clicking in your head a little bit? Is that making a little bit of sense? A little bit? Okay. Let's go back here. Here's a big, really important thing. I told you this already, but I want to put it in there. F inverse, does that mean... Does it mean it's 1 over f of x? No. I'm going to put that in there. Do not mistake -1 and f to the f inverse as an exponent. Is it an exponent? No. No. What you're going to see if you want it to be an exponent is you're going to see this. That means f inverse. This means to the -1 power. They are different. You okay with that? It gets worse. When you take more math classes, the notation gets really weird. You're like, that means times. Like, what does that mean? Not multiplication, right? Yeah, it's not multiplication. Some of you decided to multiply, which I wasn't too happy about, but that's okay. Last big fact here. The domain of f inverse is the range of f, and the range of f inverse is the domain of f. So do you remember when we found domains? You were trying to be careful of dividing by 0 and taking the square root or the radical of even radical of a negative number. Remember that? Finding domain was pretty straightforward. What about finding range? It's kind of hard, right? You have to look at it logically. It's not easy. What does this help you find? So if you want to find the range of a function, what do you find instead?
The domain of the equation.
Yes. Do you have a path to finding the actual inverse function? Yes. Do you have a very logical way of finding the domain? Yes. So if you want to find the range of the range of f of x, so what does this mean? Range of f of x is equal to the domain of f inverse. So is this really helpful? Very, very much so. The math can get nasty, though. The math can get nasty. You just have to be careful. So let's say you had f of x is equal to x cubed plus 2. If we wanted to find the inverse, let's switch first, okay? So that's going to be x is equal to y cubed plus 2. So x minus 2 is equal to? So what does y equal? The cube root of x minus 2. What's the domain of this? It's an odd root. Can you take an odd root of a negative number? Yeah, what's the cube root of negative 8? Yeah, what's the cube root of negative 27? Yeah, exactly. So actually, in this case, so if the domain is all real numbers here, what's the range up here? Yep, exactly. That's a straightforward one. Absolutely. Now, can it get a little nastier? Yes. Unfortunately, you're going to have to deal with things that look like this. Find me the inverse of that function right there. What'd you say? Perfect. You're factoring out y because you want 1y. So what does this become? Y times what? Is equal to? Mm-hmm. So what does y equal? Yep. There's your inverse. Is that exciting? Yep. You like that stuff? Okay, so your homework tonight is going to be from packet 9.